All right, let's get started. So we're just going to finish up two last reactions from alkenes, um, and then we will switch over to alkyne chemistry. So last class, I should say, we left off with the reaction. Let's just regeneralize this again. Say R1, R2, R4, sort of specify specific groups. And we discussed that there is a reaction that can actually take this molecule and basically break that alkene in half. So we can fragment the alkene completely and generate two carbonyls. Right? And those two carbonyls can be ketones, they can be aldehydes. You can eventually generate formaldehyde, which is basically a carbonyl with two hydrogens on both sides. And this probably represents one of the more difficult reactions from the mechanistic standpoint. I find that students, for whatever reason, tend to remember ozonolysis. There's a second reagent, which is usually reducing agent. The one that's often used in the textbook is dimethyl sulfide, but there's other reducing agents. Sometimes people use zinc, sometimes people use triphenylphosphine. I'll explain where that comes in. But DMS, which is dimethyl sulfide, is often what's described and is used as the sort of as the reducing agent. Okay, so the first step of this reaction is what's known as a cycloaddition, which can be kind of challenging. It's not all that different from what we saw previously with osmium tetroxide. So let me just remind you guys about how osmium tetroxide sort of worked. Right, remember that first step in osmium tetroxide, where the osmium is at the oxidation state of 8. There was basically a cycloaddition with the osmium that took place, right, where we first made a bond between the carbon and the oxygen. We then dumped electrons into the osmium, right, which then freed up these two electrons to come down here and make this bond. And so osmium tetroxide, the intermediate in it, as we sort of described, takes an alkene, you get to this sort of 5-member ring that you see here. And so ozonolysis, at least from an electron arrow pushing standpoint, the first step is actually very similar to this. Ozonolysis, if I were to ask you guys to draw ozone, and sort of on the first day of class, it may be a little bit more of a challenging sort of molecule to draw. You might be tempted to, for example, draw it in a 3-membered ring, keep everything neutral, but in fact, ozone is in fact what we call kind of zwitterionic, which means that it has a negative and a positive charge on it. So ozone, if you're actually to draw ozone out, ozone looks something like, I'm going to reverse this just to, you can do it either way, but I'm just going to draw it this way to keep consistent with what we showed over here. But this is ozone. Right, look at the extra set of lone pairs there. So as you can see, it's basically 3 oxygens, it's linear. But in order to make this work, right, and keep everything with a full octet, you would basically need to have one of the oxygens with a negative charge and one of the oxygens with a positive charge. And I think this in many ways may be analogous to maybe azides that we've seen in the past, right, where the N3, right, we've seen azides that also have this kind of zwitterionic characteristic to it. But if you think about the sort of osmium tetroxide that we sort of mentioned over here, right, I discussed, we didn't go into necessarily depth about it, but I brought up this idea of oxidation states and how the higher the oxidation state of the metal basically can be associated with how many covalent bonds are there. This is inevitably sort of tied to how electronically poor or deficient that metal center can be. In this case, we've dumped 2 electrons into it so it becomes osmium-6. In this case, there is somewhat of a parallel here. In the middle of our sequence, right, we have an oxygen, which is also, at this point, electron deficient, and it would also kind of like to take on electrons, and potentially could take on electrons in the same way as, for example, the osmium can. And so the first step in, so I'm just going to erase this, and then I'll redraw it. But this is what ozone looks like. I'll go ahead and redraw ozone from the mechanism standpoint. I'll draw it a little bent. I'll leave out the lone pairs for now. Sorry, I said before, I'm sort of, as I drew this sort of osmium, it's linear. It probably actually should look like that, right? If you think about it, it should actually be bent. I don't know why I said it was linear before. If you think about it, what's that? Yeah, it should be trigonal planar, right? It does have the lone pairs here. That oxygen is sp2 hybridized, right? So this should, in fact, be more like an alkene in terms of the geometry. So I kind of drew it before linear. It's probably, that was a mistake on my part. I shouldn't have drawn it that way. This is more likely what the geometry should be. And what will happen is if we push the electrons in the same way that we did over there, right, we're going to push the electrons almost identically here. So once we make that bond between the carbon and the oxygen, we can now dump electrons into that oxygen, right, which is now going to make that oxygen neutral, right? And then what we're building up over here on this side of the carbon, right, the electrons are going away from it, so that's going to become what charge? It's going to begin to take on a positive charge, right, because it's losing the electrons. And then nearby you have the O-, which can then attack, right? And so what you form in the first step of ozonolysis is a sort of a 5-membered ring. And I think from the standpoint of electron arrow pushing, I think students in general will often be able to get here, then it's not a big issue. The next part of ozonolysis is the one that is, I think, a little bit more tricky, and it's the fact that before you treat it with DMS, there's actually a rearrangement that takes place to get to a sort of peroxide looking like intermediate, which is a little bit more steppy, and I'll show you it. Give myself a little bit of board space here. And what ends up happening is you actually crack this back open. And again, not to say that this step that I'm going to do here is thermodynamically stable. It's probably uphill. The intermediate, what I'm going to show you, is going to be uphill. But the net result is the end product, there's going to be sort of a retrocycloaddition followed by a cycloaddition, which I'll show. You may ask why the first step is going to happen. It's, again, it's probably going to be an uphill energetic process. It's just that the intermediate is lower energy. And what's going to happen here is that we're actually going to open this up, okay? So we're going to make a double bond here. We're actually going to break this carbon-carbon bond. And we're going to put the oxygens up here. So what's going to happen is this oxygen is going to be a double bond, which means that oxygen is going to be what? It's going to become positively charged. That oxygen is taking on electrons, which means it's going to become what? Negatively charged. And then what's going to be over here? I'm going to have formaldehyde, basically, right? So I've left out the R groups here for simplicity. And to be quite honest with you, if you were just trying to understand how this reaction works and trying to rationalize how ozonolysis behaves, we could probably just stop right here and not actually go to the sinkhole intermediate, because this has done the job that we wanted to do, right? This has broken the carbon-oxygen bond, carbon-carbon bond, and resulted in something that's very similar to what we have here. And if you took this intermediate that you see here, you were to treat it with dimethyl sulfide, which is here. Dimethyl sulfide is actually fairly nucleophilic. The sulfur is able to take on a positive charge, and you can actually generate a molecule called DMSO. And so what you could, in principle, at this stage do, and you can use this to rationalize it, which is probably more important to do at this point, is that you're going to reduce that molecule and you're going to end up with what's called DMSO. Do you guys remember hearing about DMSO? You guys seen that before? DMSO? DMSO is an extremely, extremely polar solvent. It dissolves a lot of things, and it's highly useful. It's actually often used for, what's that? Yeah. So you're just saying that it accelerates SN2 reactions. Yeah. No, but what I was going to say is it also is used, I know a lot of you guys are like pre-med and pre-health. DMSO is often used for like administering specific drugs that like go through the skin. So they'll take like a drug up in DMSO, you'll dissolve it in it, you'll put that on the skin or whatever, and it will go through your skin and end up in your bloodstream. For those reasons, DMSO itself isn't bad, but if DMSO has bad stuff in it, that can be bad. But usually, obviously, in medicine, it's used in a positive way. And so you can sort of rationalize this mechanism from here, but it turns out that this isn't the intermediate that takes place. This will actually rearrange and reconnect. And in truth, what ends up happening is that you do this. And you get to this intermediate that you see here. And this is called an ozonide, and it's basically when you run ozonolysis before you add DMS, this is actually the intermediate that you get. And so when you then take this and treat this with the DMS, what ends up happening is that then attacks the peroxide. You get your product plus your DMSO. So again, it's a fairly complex mechanism, especially when you take into account the sort of ozonide intermediate as well. It sort of increases. We got a lot of reactions now. Again, I would put this towards the tail end of your, sort of in terms of lining up your ducks. Knowing the ozonolysis mechanism should certainly be at the back end. If it shows up on an exam, it will be one of the more grand challenges questions that will come up that will be related to it. So if you're ahead and you have time to study this mechanism, get it down, certainly do that. If you're behind right now and still have a lot of other things that you need catching up with and you're struggling with some of the other more basic mechanisms, don't worry about this. This isn't going to affect, knowing this mechanism isn't going to affect your ability to pass this course. Okay? So there it is. This is ozonolysis. Now there's one other reaction that the book also brings up that can also get you here that I'll just sort of mention very briefly. And in fact, given the time that we're looking at right now, I probably won't even bother going through the mechanism of this one. If you want to look it up, I won't bother holding you guys responsible for this mechanism I'm about to show. So I'll tell you I won't put it on the exam. But, well, the first step I will. So the first step, it turns out that if you take an alkene and you treat it to osmium tetroxide, which we were just talking about, followed by sodium borohydride, right, we end up getting we get the dihydroxytropyl, we get sort of the 1,2-diol that you see here. So this is a reaction that you guys know. It turns out that if you take this, you treat it with a reagent called choroidic acid, which is HiO4. You will actually get to those same ozonolysis products. And so I'm not going to go through the mechanism of this. If you guys want to learn it, you can. But I know that we've had a lot of new mechanisms come up, and I'm going to try to cut down at least one that might not be It's actually fairly analogous to the osmium tetroxide in many ways, so certainly feel free to go through and read it if it helps you, but I know that we've got a lot of mechanisms coming up here, and so I won't necessarily hold you responsible for the pyruvic acid from the mechanism standpoint, but certainly know it from the reagent standpoint, so you'll just have to sort of remember. If you want to learn the mechanism, I'm not quite sure that knowing the mechanism is going to help you memorize this one. Yeah. We haven't, so you're talking about like epoxidation? We haven't discussed epoxidation. Yeah, no, that's, yeah, the peroxide. Let's, no. I don't think that's in this chapter. I don't have it written down. So no. I think there's an entire chapter on peroxides, which is one that comes up. Yeah. But it's really, you know what, that's good because you sort of recognize the interconnection there. So. Okay, so all right. So it might be in this the actual synthesis of the whatever. We'll probably get to that later on in the semester, but don't worry about it for right now. Okay, so that's basically it for alkene chemistry. And so there's a lot in here, as you guys can clearly see. This is where the course is starting to get heavy, right? A lot of information. A lot of those specifically on the first day, really try to tie them together from the mechanistic standpoint. But some of these more recent mechanisms are a little bit more challenging, and we can certainly rationalize them. Certainly urge you guys that are ahead to get those. But again, if you're struggling to get some of the more basic stuff, don't worry about the more challenging mechanisms. Sort of more try to get your head around electron arrow pushing more generally. So we're going to move forward to alkynes. Okay, and the nice thing about alkynes is that a vast majority of this chapter is going to deal with chemistry that's highly analogous to alkenes. And so we're just going to be looking at them in the context of what would happen if you did the chemistry of an alkene on an alkyne. We will evaluate the mechanism of that, so we'll go through the mechanism of some of these situations based upon what we know from alkene chemistry. And then there's just a few little, I don't want to call them twists per se, but there's just a few little additions that we'll have to consider to sort of understand it more generally. And so as you guys, the sort of first addition that we'll get to in a second is, I'll get to once we sort of go through this, but it's just on the surface, what do you guys think would happen? The very first reaction we learned with alkenes, right, was taking an alkene and treating it with acid and water, right? I think that was the first one that we talked about. So if you took an alkyne and you treated it to HOSO4, let's make this, just because there is regiochemistry associated with this, I will make this an alkyl group, and I will just make this a hydrogen, so this is some group, just so that we sort of remember our Markovnikov addition. But if we took this molecule and we treat it with sulfuric acid, which again I like drawing out in this way simply because it helps me break that bond, right? So that's why it's OSO3H. And we just play it analogous to what we did with the alkene. What's going to be the first step of this? Instead of the double bond reacting, it's now the triple bond that's going to react first, right? So we learned in the alkene chapter that the alkene double bond can serve as a base, right? So we're going to take a couple of the electrons that are in here, and we're going to protonate it, right? And just as we discussed with alkenes previously, when we protonate this molecule, that proton can end up on two possible carbons, right? And the two possible carbons are this one here, or that one there, right? If we just think classically for the mechanisms, there are these two possibilities, but we also learn that one of these carbocations is much more stable than the other, right? So which one of these two is more stable? First one, right? It's more substituted, right? More substituted alkene more substituted carbocations to be more stable carbocation. We've seen it in the case of sort of sp hybridized, things that don't necessarily, sp2 hybridized carbocations, or ones that have all sort of single bonds around them. This is a little bit different because it's kind of an sp hybridized carbocation, so perhaps I should have that straight from that standpoint. But this will be more stable. And so if we were to complete this mechanism analogous to what we saw with our alkenes, what's going to be the second step of this reaction? Yeah, the water is going to attack, right? So we're going to get our H2O is going to attack. Right? We're going to end up with water attached to that carbon. Again, it's the oxygen-carbon bond that we're making. I've simply redrawn the water here to sort of set myself up for the final step of the, at least first part of this mechanism, which, again, depending upon what you want to have deprotonate here, you can have the water deprotonate. It probably is the water that deprotonates it. You can have the sulfonate deprotonate. It doesn't matter which one you use. I often like to use the conjugate bases just to bookkeep. So that's what I'll do. Right, and we would say, oh look, this is the molecule that we're going to make. And so some of you, if I gave you this reaction, and I asked you what the product of this reaction would be, at this stage of the game, it would be perfectly reasonable for some of you to predict that this would be the product. And I would be very happy if you predicted that that would be the product, even though that is not the product that's going to form. But you see the analogy here, right? The reason this is not the product that forms, how you rationalize that this is not the product that's going to be formed, can be in one of a few different ways. Any thoughts? Yeah. Well, let's. I'm going to come to the keto enol tautomer later, but just. Do you think? What do you guys think would happen here? If I had this molecule, I still got sulfuric acid, I still got water, and guess what? I still got an alkene, right? And so, and in fact, what do you think is a more nucleophilic or a more basic alkene or nucleophile, like set of lone pairs? Turns out that when you have oxygens, right, those lone pairs can actually make that a very good nucleophile. And so there's really nothing to stop this from reacting with sulfuric acid again. Does that make sense? Right, so we've done the reaction, but we still have lone pairs here. And so those lone pairs can react again with a second, not a second equivalent because we've in fact regenerated it, but it can re-react, right, with the sulfuric acid. The product that we would get would be that molecule that I've shown there, if we simply hold it to that. Does this look like it's a fairly stable carbocation? So some of you might look at this and you might say, an oxygen is electron withdrawing. I don't like having an oxygen next to a carbocation. In fact, you should love having an oxygen next to a carbocation, because what can you do with that oxygen? It is not only electron withdrawing, but it has something that becomes one of these real golden rules of it. Yeah. What's that? What about the lone pairs, Aisha? You got resonance forms, right? And let me ask you guys, maybe I'll ask you, Aisha, once I draw it. So there is a resonance form there. You're absolutely right, there is a resonance form. And this is one of the reasons why oxygen can actually help stabilize these systems. Those lone pairs can basically, in essence, be back donating into this double bond, helping make it a bit more of a nucleophile, because at the end of the day, you can imagine this resonance form, and Aisha, which of those two resonance forms do you like better? Well, at this point, again, we're still trying to develop these habits of the things that we really like, but at least if your answer is grounded in some real chemistry, I'll be happy. So what do you think? This has a full octet. What about this one? This one does not have a full octet. I don't know where you were pointing initially, but some of you may say, well, oxygen is more electronegative, right, than carbon, so I'd rather put the carbocation here. And again, this is what I was saying, is that that's rational, but we have learned and we are seeing time and time again that this sort of ability of molecules to have full octets is really a driving force. So that is what really trumps the potential resonance forms here, and this ends up being the more stable resonance. What might we do to finish up this mechanism now? Aziz, what do you think? We've got a protonated oxygen there, right? We can finish up this mechanism. At the very end of it, we probably want to get rid of that, right? So we want to do a deprotonation event to finish this up, right? And so what we'll do is we will take our, again, you can use water here if you want, but again, I'm going to push the electrons from the base, and then I'm going to move the electrons in here onto the oxygen to give those electrons to the oxygen. And through that process, find somewhere on this board that I have space, the product that we are going to form is going to be this one there. So as it turns out, when you take an alkyne and you treat it to acid and water, it does exactly what you should think it would do. It goes to this, but then it keeps going, right? Now, one of the things that's important here, so do you guys understand this? Does this make sense? Right, you have an alkyne, you have this alkene that can still react with the acid, and then over time you end up getting back to the carbonyl. Okay. So now one of the questions that you guys might ask, and this becomes kind of important, is we have this molecule here, and we have this molecule here, which is the intermediate. Both these molecules have the same molecular formula. They both have the same amount of, water didn't re-react with this. Yeah. A hydride shift from the carbocation?
No. It's like those two intermediates. Like the difference is like
this intermediate and what intermediate?
And the one I'm doing.
What?
The
product.
The fine, yeah.
Okay, so.
Like from there to there, you could see the double bond kind of.
You're talking about like wacky sigmatropic rearrangements that are actually not even thermally forbidden, but you would have no reason to understand why it would be thermally forbidden until you took a more advanced organic chemistry course. So the errors that you may want to do there, I would just avoid. It's not that they're wrong. You can, in fact, do what I think it sounds like you're trying to do, but that's more advanced stuff. So, but looking at these two molecules, you may recognize that these are isomers of one another. And as is the case with a lot of reactions, right, we talked about how certain things are driven in one direction or another based upon, say, putting water into this reaction, right? We could potentially go in the reverse by dehydrating the reaction. So on the surface, you guys sort of nodded your head as I was kind of going through this process here. But the realization is that you could also go in the reverse, right? We could protonate this, and then we can go to the carbocation, and then we can do an elimination back. And so for those reasons, there is this sort of equilibrium between these two species. And so this becomes, I think, maybe one of the first sort of new things to sort of understand and appreciate within the alkyne chapter. And that is ketones and carbonyls are in general highly favored thermodynamically. Again, I don't want to get into the sort of specifics of why this is the case, but there are very few instances where, for example, a ketone, where a molecule would rather be what we call an enol. This is what we would call an enol. Any ideas why we might call that an enol? You're all saying it right. Say that again, please. Well, so let's look at the two things. Ene, alkene, alcohol. So it's an enol. So it's just the clever name that they came up with. So this is an enol. And this is clearly, I don't know if you guys know this. This is what we would call a ketone. And in general, so I want to get to this idea of, so here's the mechanism, but I just want to sort of make a point here about the relationship between these two molecules. Because they can interconvert with one another. You can use the mechanism that I showed you here to interconvert. You don't necessarily need a super strong acid for this interconversion to take place. Oftentimes it's very difficult to keep an enol stable, like even with just maybe the water, the moisture that's in the air can often be enough to sort of facilitate the transition from one to the other, or even they can react with one another to sort of form. So the ketones are a very downhill process. This idea of enol ketotautomerization, which is the name that's given to this, one of these things that you guys are going to need to know and appreciate. So for most cases, reactions will highly and strongly favor the keto form. There's reasons associated with the dipoles of these molecules, for example, that do this. But what you should recognize is that these do interchange very readily, and they don't need necessarily the strong conditions that I pointed out earlier. This will be in equilibrium. It generally favors this direction. There are a few instances where molecules, you know what, no, I'll get to that next semester. So for now, just appreciate that, okay? Ketones, and we'll see this time and time again. Carbonyls, thermodynamically stable. For these reasons, these are almost always favored over that. Yeah?
Can you just give us a sign of teaching World War II next semester?
I'll teach you that next semester. I don't know, maybe. Maybe you'll come by for office hours. But actually, so that's that. But let me ask you guys a different question. So, what do you guys would think would happen instead if, I mean, at this point we can begin to sort of imagine some other reactions that we can do. So what are some of the other reagents that we use? Well, the quick one that kind of extends from, again, I'll just choose this as the generic acid. Sulfuric acid, and now instead we use an alcohol, right? I'm not even sure if this is in your book. In fact, I don't think it's in your book. But let's do it anyway. Let's just think through it, right? I don't actually even have it in my notes. I'm just sort of. But let's discuss this. Just I don't think this is in your book, but let's just discuss it formally because it's, it's a good sort of practice. What would happen here, right? First step is going to be the same thing. Now instead of water adding, you're going to get this R1, R2, OR2, right? It's going to be protonated, and what can happen here, right, is that we'll basically do the deprotonation. And depending upon the system that you have, so I'll just say -H+, you guys should be able to do that at this point. you get to a slightly different molecule now, right? It doesn't necessarily have the proton that we had earlier. We have what we call, and this is also an enol kind of ish, but it's not really an enol. It's what we call a sort of an enol ether, because it's it's an ether linkage. So this is an enol. And if we were to continue on this reaction, as you might imagine could happen, there's one fundamental difference in this. And actually, because this isn't your book, I'll just maybe convince yourself of this mechanistically, because we do have other stuff we could get to. But if we kept going, and maybe you guys can practice that on your own, because again, it isn't your book, I don't want to waste too much time on this. But you could potentially stop at the enol ether, but maybe if you only have one equivalent, for example, of alcohol in there, you might stop here, but if you have a second equivalent, you can go to a molecule that's called hemiacetal, which will be discussed, perhaps by me, next semester. But clearly you can kind of see, and I would hope that you guys, even though this isn't in your book, this might be a good practice mechanism for you guys to try to say how with this and a little bit more acid and water, a little bit more acid and alcohol, you should be able to get to that molecule there. Okay? All right. I feel like I'm just going through the same stuff over and over again at this point, because a lot of this stuff kind of is. What was the other acid that we used? So we did acid in water, we did acid in alcohol. What was the other acid that we used to add things across alkenes? Acid in water, acid in alcohol. What was kind of the third one? Sitting? Well, no, I'm talking about with the Markovnikov addition. So with the acid in there. There was one more acidic-ish reaction with alkenes that we looked at. Not the mercuric acetate one. I mean like bronzed acid. One more bronzed acid. Come on, someone. What's that? No. Someone. Come on. HBr. Or Right, HBr, right? The other one that we had, let's say, was HBr or HCl. No, I said aside from those. I got it videotaped. We'll find out. So if we have acid, and the alkyne, we know that if we have HBr, HCl, HI, they will add across this double bond, right? Again, you guys should be, again, I'm sort of going over, as you notice, and doing the same thing over and over again, right? I'm adding across the alkene. Some repetition here. I generate that carbocation. I have Br minus. Nalda, what do I do now? Nalda, you Nalda? Nalda, what do you do? Well, we want to kind of get rid of the positive charge. How have we been generally doing that? We're not going to necessarily get rid of the positive charge. We're simply going to, as is the case, we're kind of shifting the charge potentially somewhere else. And in this case, this whole system is conservation of charge. That whole system is neutral, right? So we don't necessarily need to, we can sort of cancel each other out here, right? What if just the bromide attacks the carbocation, right? So if the bromide attacks the carbocation, right, and this is just like adding HBr across a double bond, except that now we still have the alkene there. And in fact, if you used one equivalent of HBr, you could stop here. So this would be the product. With one equivalent. have a second equivalent of HBr, what can happen? We still have our alkene there, right? So because we still have our alkene, we still have something that can react with the acid, right? So these electrons will react with HBr. Again, the analogy that we drew with the enol ether here, right, is that we're going to protonate this carbon. Right, we're going to protonate that carbon. We have a carbocation. Aisha told us earlier, when an oxygen's there, the oxygen allows us to have a resonance form, right, that has a full octet, as she said, which makes it a more stable resonance form. For these same reasons, the bromine, even though we don't necessarily think about bromine in this way, the bromine could also donate its electrons. I'm not going to bother drawing that at this point, but realize that there is a resonance form here as well. And that will, again, help explain why the regioselectivity sort of maintains Markovnikov, right? You get the Markovnikov, and then you get a second Markovnikov-ish addition, which now the bromine attacks, right? So the bromine's going to attack. And now we have the geminal dibromide, which is if you have two equivalents of HBr. Okay? So again, we've just learned 3 reactions, maybe 4, depending on how you count it. If you want to say 1 equivalent of HBr is 1 reaction, 2 equivalents of HBr is another reaction. You know, we've learned a bunch. We've learned some chemistry. Yeah.
Would you have to tell us the question you had?
If I leave it out, if I forget to, depending upon, you may want to ask me. I would tell you. I'm not going to expect you to read my mind, but
Your bond, I'm assuming you want us to go over
who knows? Who knows? So if I say it on a quiz or something like that, I will accept either answer if I don't specify. If I specify, if it's on an exam and it seems like it's part of a more complicated question where understanding if it's 1 or 2 might be important, and I've mistakenly forgotten to say how many equivalents, definitely ask, and I'll make an announcement, because I will try to make sure that I do that. Okay? All right, so does it make sense? Okay. All right, so that is HBr. You guys want to pick another reagent? Huh? What? Well, no, of course I'm going to keep going. My question was, Aziz, do you want to talk about another reagent that worked on alkenes? So we had acid and alcohols. We had HBr. HCl would be the same thing, right? HI would be the same thing. We don't need to go through that. You guys should know that. So that's you read my mind, right? So Br2, right? Another thing that we saw add across alkenes is Br2. So what do you think would happen with Br2? And I'm going to, in this case, actually show, I'll just say R2 over here, because we can actually get some stereochemistry here that will be important. But since you brought up, what's your name? Irina. Okay, so Irina, since you brought up Br2, let's go through the mechanism of the Br2. So what's going to happen when that alkene first reacts with the Br2? Okay, so I should probably draw out my bromine, Br. And I'm going to be pushing electron arrows, so I'm going to be illustrating the flow of electrons. So where are the electrons coming from and where are they going to go to? Right, so again, pay attention to the direction in which my arrows, if you're still struggling with electron arrow pushing, pay very, very close attention. I'm going, as Irina said, I'm going from where the electrons are to where they want to be. They are going from this bond to the bromine. I'm not going to stop there because then I would have, well, bromine you can exceed bromine's octet, but we don't want to do that, right? Because the reason why we're attacking is we like our leaving group here, which is Br2. And again, if we want to jump right to it, which we probably will given the time, again, depending on how you want to go through this, if you want to draw the bromine and the cation and then show the sort of the pseudo-resonance, I'm going to go right to the bromonium because this is important, right? Previously, we went to the bromonium and we explained why the bromonium intermediate was important because bromine adds across. How? It's got anti-addition, right? You have one bromine end up on one side of the double bond, you have the other bromine end up on the other side of the double bond. So is that going to change at all with an alkyne? So what's going to be how's it going to behave with an alkyne? So Irina, what do you think? If we're going to attack, where are we going to attack from? Absolutely. And what's the result of that going to be? And again, we can attack from either side right now. But the stereochemistry basically means the bromines are going to be trans to one another, right? So one bromine is going to be on one side of the double bond, the other bromine is going to be on the other side of the double bond. And that's going to be our product. I don't have it written down here, so maybe there's a reason why it doesn't happen, but I guess, you know, I would assume that if you really took a whole bunch of bromine at this guy, and maybe it's, you know, certainly if you just use one equivalent, you would get here. Maybe if you use two equivalents, although I don't have it written down, so maybe it's not discussed. But if I added a second equivalent, at least mechanistically, you could imagine getting to 4 bromines on those bonds. I don't know if that's something that requires a lot of heat or something, but obviously that's something that you guys can imagine doing as well. But I don't have that in my notes, so I'm guessing that's not in your book. So, but again, you could probably mechanistically, I just want to sort of make that point because we did discuss that with the other ones. And it's certainly rational to think that it could happen here as well. Yes? Like what?
The step 4. I was still drawing the intermediate the same
With the carbocation? With the carb, I mean that can be helpful. Remember, so I think Sam was asking wherever Sam is. I saw him walk in. Oh, there he is. So Sam was asking this earlier. The carbocation intermediates are helpful to remember the regioselectivity. So it's kind of tough because you have to know both, right? So showing the intermediate that you're talking about is fine, and in fact, the intermediate that you're discussing is the one that can describe the regioselectivity. As long as you don't forget that it has to come from the opposite face, it should be fine. If I ask you a question, though, that's sort of asking why the stereochemistry is what it is, you should probably show it in terms of attacking from the backside attack. So, you know, again, they're both helpful and they're both useful and neither of them is wrong. They both tell us different things. One of us tells us about the regiochemistry, the other one tells us about the stereochemistry. So depending upon which one of those in a question seems to be more important, you know, that's sort of how you should think about it. All right, so we're charging through. So that is bromine. Okay, so so these were the kind of, and then again, I don't have it written down. But what if we use bromine and alcohol, right? I mean, just think through that. I'm not going to go through that right now given the time, but, you know, it should be the same thing, right? And then you just have to consider the regioselectivity in that case. So actually the bromine, the regioselectivity doesn't matter, right? Because it's bromine on both sides. Just going back to what you were saying earlier, the regiochemistry that your thing would more likely illustrate would be if there was alcohol in there as well, right? Because the regioselectivity, where that carbocation would rather be in a bromonium type species, the more stable carbocation would ultimately be where the alcohol would want to go. So that's the analogy there. I'm not going to go through that right now, but you guys could probably and should be able to sort of know that, so you might want to consider that, but again, I don't have it in my notes, so I'm guessing the book doesn't discuss it. All right, what the book does discuss, though, is going back to Markovnikov versus anti-Markovnikov. So in the same way that we learned that acid and water can add across an alkyne or an alkene in one way, there was another way that we learned that you can add H2O across double bonds the other way. Do you guys remember what those reagents are? Somebody that doesn't speak that much and someone that doesn't speak, someone that doesn't. So what's the reagent that can add H2O across a double bond with anti-Markovnikov regioselectivity? No. Madison. I'm going to start calling by names on shirts, because I don't know your name. Do you remember what the reagent is that adds water across a double bond anti-Markovnikov? See hand right there. What is it? BH3. That is correct. Remember that, guys. The association here has to be, you know how to add water across one way. The BH3 for association, because again, these are going to pile up. You need to have some sort of association to keep them all together. So it's BH3, right? So this is important that you guys remember this. So if we have BH3, there is one other reagent that we need following the BH3, and that is, do you remember what you need? H2O2, or sodium, yeah, basically, yeah, H2O2. Yeah, usually it's technically the sodium, it's the sodium version of it, but basically it's hydrogen peroxide, yeah. So this is going to simply add the alcohol. I'm not going to go through the mechanism of it, given the time, but we do know that the borane adds across anti-Markovnikov, and so when we add across and we oxidize it back down, we're going to get that. Now I'm going to sort of go back 15 minutes ago when we were discussing this type of molecule. What is this kind of compound called? An enol. And what did we learn about enols? They're not happy as enols. They'd rather be ketones, or in this case, it's technically not a ketone, but it will still be the carbonyl. But this is when you have a carbonyl that has a proton at one position. So we'll just say it's the carbonyl. This is the aldehyde, right? And the aldehyde, it's the same kind of concept, right? Aldehyde is simply the name that is given to carbonyl-containing molecules that have a proton on one side and a carbon on the other. So it's kind of it's the keto-enol tautomer, but technically it's not a ketone, it's an aldehyde. So ketones are when there's carbons on both sides. But yeah, so again, if you understand the keto-enol tautomer, right, and you remember borane and peroxide, right, then you just put them together and you should be able to predict sort of what happens in the case of an alkyne with them. Now here's the one little thing about, so borane is the reagents that we learned previously, and I'm not a stickler for this, but I'll bring it up because people often ask it. There are some challenges that are often present with alkyne chemistry, and specifically with some of the regiochemistry associated with alkynes. As you might imagine, we've discussed how sterics and so forth, like there's a linearity to sp hybridized atoms that become much less or much more sterically unencumbered. And so as it turns out, a lot of the features that influenced borane addition across a triple bond, that added across a double bond in that way, might not necessarily be as good with alkyne. So technically, if you read in your book, you'll see this SIA borane reagent. I'm not going to worry about that. If you remember it and you use that, that's fine. There are things that were worked out, and so you can remember that if you would like, but I'm perfectly fine with you just sticking with the borane because I think you guys got a lot of reactions, and I want to make sure that you can associate them as much together as possible. So just the borane is perfectly fine. If you want to use the other one, that's fine as well. The important part is that you have a BH in there. Okay, does that make sense? So you'll see there's another reagent that's specific for alkynes, but my opinion is that it doesn't, at this stage of the game, it doesn't matter. Okay? All right. Okay, so we're making good time. So, all right, so, another reaction, again, is kind of neat, right? It's kind of nice, right, because we're refreshing on the reactions that we learned previously. So I'm going to ask a question in a little bit different way here. Based upon what you guys learned about alkene chemistry, how might you do this? We want to add hydrogen across triple bond. We want to do it both. What reaction might you use, and not somebody that doesn't say that much? You're looking back in your book. Do you remember what the reagent was? If we want to take what's that? So that's if we want to add a proton and then something else. If we just want to put 2 protons. If we wanted to do this. One of the last reactions that we learned last class. We learned how to take an alkene and reduce it. So basically add hydrogen H2 across the double bond. Somebody else. You add H2. Yeah. What's that? It is the metal. Oh, so you're not getting into like nickel. No. So you're getting a little bit more detail oriented. So you're right, it is a metal, but there's something we need. Right? It's not just the metal. We need, the metal doesn't have 2 hydrogens. What does have 2 hydrogens? Hydrogen. Right? So hydrogen has 2 hydrogens, right? H2 has 2 hydrogens. And the metal that we discussed, so hydrogen gas and a metal, right? And what we learned with alkenes is that there's a whole bunch of metals, but the sort of go-to metal that people often will describe is palladium on carbon. So this is kind of the classic reducing agent. It's palladium on carbon. Platinum can sometimes do this. There's a whole host of different transition metals that can do this process, but palladium on carbon is generally the go-to metal. Now, what's cool about, and if you did this reaction and you treated this to a balloon of hydrogen, palladium, activated palladium, palladium over activated charcoal, you would reduce that. So again, that should be completely analogous to what we saw with alkenes, right? You treat it with one equivalent of hydrogen, then you do the same thing with another equivalent of hydrogen. Now, we have to do this twice, right? And if we think about it, we discussed the stereochemistry that would result from reduction. You remember this? I mentioned this towards the very end of last class. If you have an alkene and you're reducing that with hydrogen, they add from the same face. Remember that? So, for example, if we have, I showed it with like a 6-membered ring with 2 methyl groups on there. And if you reduce that, the methyl groups end up in the same position because the hydrogens are coming from the same face. You guys remember that? And so if you did that on an alkene, right, what would happen? If we were able to stop this and add it from one face, we would get to that. That is an alkene with specific stereochemistry, right? It's going to have cis stereochemistry. And under the reaction conditions that we've shown, that cis stereochemistry doesn't matter because the second equivalent of hydrogen just comes in and adds another equivalent of hydrogen across it, right? But it turns out that you can do this. And this is another one that's perhaps a little bit easier to remember. And usually what I will tell people is it has a name, and it's called Lindlar's catalyst. If you can remember that, great. I will settle for poisoned palladium, because that is really what Lindlar's catalyst is poisoned palladium. And really all that poisoned palladium is, I think in the case of Lindlar's catalyst, it's like quinoline or something like that. And what it is it's a basic residue that will, in essence, soak up some of the sites of the palladium and make it less active. And you can definitely take Lindlar's catalyst and you can over-reduce molecules if you push it far enough. But what the Lindlar's catalyst will do is it will slow down that reduction enough such that you can in fact stop it at this. So it's the exact same thing. It's basically this, except it's been poisoned a little bit with some quinoline, and I think there's some other derivation to it as well. There's one other thing. But basically what they've done is it's called Lindlar's catalyst. But again, it's just been poisoned so that it's not as active, and so they can basically allow the reaction to stop at the double bond. So that's what's important there, is that you recognize that palladium and carbon adds syn. You see the result that can have on alkenes with stereochemistry. In the case of the alkyne, if you reduce twice, there is no stereochemistry, so it doesn't matter. However, the alkene that you generate could have stereochemistry, and thus it's important to realize that the syn addition can potentially lead to the cis double bond. Does that make sense? Somewhat? Okay. So palladium and carbon takes you all the way down. You poison that palladium on carbon. You get to something a little bit different, but mechanistically it's just the halfway point to what would have otherwise been formed. And so everything that we've done up to this point is quite literally the alkene chemistry applied, the alkene chemistry applied to the alkyne chemistry. Now, in the same way that, one of the ways that you should remember borane adding across the double bond one way, and acid and water adding across the other way, sometimes those can be associated. The next reagent is going to be the complement to what we're seeing here. And it's going to be a little bit different mechanistically. But the question is, if I can reduce cis, great, I know that these reagents will lead to cis. And what you should remember is that there happens to be another method that can lead to the trans. Okay, and this mechanistically we'll go through. It's a little bit more complicated. It's not necessarily anything that you guys would know intuitively or be able to predict intuitively like some of these others, but lo and behold, there it is. And at least maybe one of the ways that you guys can remember this is what is the thermodynamically most stable, what's thermodynamically more stable generally? Is cis-alkene or trans-alkene? Trans-alkene, right? The groups are further away from one another. So you guys should be able to remember that a trans double bond is more stable. And in fact, the conditions that we're going to use to generate a trans double bond will allow us, in fact, to access the trans orientation. And mechanistically, it's a little bit of a doozy, though. So bear with me. So sodium and ammonia, you're going to see, well, there's a bit of confusion here because we're going to see NaNH3 in about, hopefully I can get to it today, there's another reagent called NaNH2. And there can be a little bit of confusion here. Just pay attention to the fact that the charges and everything else like that, but NaNH3 are the conditions that will lead to a trans double bond. This is a really cool reaction. In fact, when I was in grad school, it was one of, well, I used lithium instead of sodium, but it was one of the very first reactions I ever ran. What happens is if you take sodium and you put it in ammonia, you actually end up getting this deep blue color. So you do this usually, so the ammonia boils at like -33, so you basically have to cool down the ammonia and condense it at like, in like a dry ice acetylene bath at like -70, so you have this liquid ammonia. And in that liquid ammonia are like pieces of, in this case, sodium. Sometimes people use lithium. What will happen is the sodium will dissolve, will basically dissociate in the ammonia into sodium and a single electron. And so that deep blue color that I described is actually the electrons that you're seeing in there. It's this really beautiful color that you see. And so a lot of the chemistry with sodium and ammonia is going to be a little weird because we're just going to start throwing electrons at this molecule. And so I'm just going to start drawing dots, which represent the electrons. Now, if I were to start that process and say, here's a little electron, and I were going to react that with that double bond, based upon what we saw in the past from our sort of homolytic bond formation and bond breakage mechanism, this is when we have to revert to those double-headed arrows. Remember this? Right? And so what I'm going to do is I'm going to make this bond, I'm going to take the bond that I have there. On one end, I'm going to form two electrons. What do those two electrons become? If I just are making two, what are two electrons? Well, they could be a bond, but if they don't have anything on the other end, they are lone pairs, right? So when these react together, they're going to become a lone pair. On the other side, we're going to end up with another radical, right? And what's really wild about this is that now we have a charged system, right? That electron is negatively charged, right? It is the negative charge, right? So we've got this sort of anion with the radical here. And what can happen here is, in fact, the radicals themselves. This is kind of bizarre. It'll come up again a little bit with, it'll come up a little bit when we start getting to amines. Amines can sometimes do this as well. But if you think about it, when you have that radical there, it's not necessarily a full-blown lone pair, and I get that this can be a little bit confusing, but just take my word for it. That what can happen here is you can actually undergo inversion of this stereochemistry. So you can basically do what's called a radical inversion. The radical can go from one side of this bond to the other. Okay, and I get that this is not something that we've seen in the past, so you're going to kind of have to just believe me on this. Right? And one of the ways you can rationalize this is that it's maybe not a full-blown sp2 hybridized carbon because it's not really doesn't really necessarily have all of its electrons. Maybe it's somewhere in between the sp2 and sp. And then it's going to pick up a second electron. You get to the dianion. It may be protonated first. It probably is protonated first, but let me just get through this because I think you guys could probably figure out the rest from here. If we have, you can either protonate it here, you can either protonate it here, you can protonate it before there, but I'm just trying to make the most important point of this. It probably does never actually get to this dianionic form, but at this stage, what's going to happen? We need to pick up a couple protons, and where are those protons going to come from? The NH3, right? So at this point, the NH3 serves as our acid, and again, ammonia is an acid in name only here. It's simply giving up its protons. So the NH3 will ultimately serve as the proton sources for these. So one of the byproducts of this reaction will be sodium amide. Okay? Does that make sense? And again, you should probably protonate here first. But again, the important point here is that sodium amide reduction. The point that I want to try to make here is that when you generate this radical here, You can invert it. That allows you to go to the more thermodynamically stable trans species, which explains why stereochemistry is what it is. Okay? All right. One more thing I wanted to get to. Okay, the last thing that I want to mention, and this, I think, and then if there's anything else to deal with, we'll finish it up next class. But this will be the bulk of the most important alkyne stuff. We've gotten through the majority of the stuff that I want to cover. But if you guys remember a while ago, I have these numbers off the top of my head, but I'll give you rough estimates. Right? We basically saw that if you have like so sp3 hydrogens, I guess whatever it'll say R, so sp3 hydrogens, that's not acidic at all, right? This is, pK is in the 50s, right? And if we have an sp2, where we have maybe like a double bond, that's really a little bit more acidic, but it's also really not very acidic, right? It's maybe the high 40s or maybe still low 50s. I don't remember the specific numbers. But the moment that you jump down to sp2, and again, we did mention this the moment that we jump down to sp, and we go to, for example, an alkyne, alkynes become much, much more acidic. The pKs of these are in the high 20s or low 30s in that ballpark. So you see tens of orders, you see basically a huge, huge, huge increase in acidity. And what that means is that alkynes can be deprotonated by strong bases, and this is what I was saying earlier, can sometimes be some confusion. NaNH2, again, not to be confused with NaNH3. NaNH2 means the amide, so the negatively charged nitrogen, can in fact deprotonate this and lead to the sodium acetylide, okay? Take the sodium acetylide, we can now treat that with any number of different electrophiles. We can now intercept SN2 chemistry, for example. We learned that, for example, azides and cyanides are really good nucleophiles because they're sp hybridized. And so you could, for example, take a molecule like this and treat it to, this is 2, we could say, for example, treat it to an alkyl bromide, and now we can begin to generate sort of more substituted triple bonds. Next class, if I remember the syllabus correctly, I believe that next class is when we're going to start talking about synthesis. We're going to be able to start talking about, we've learned enough reactions now where we can begin to start talking about taking these reactions and putting them together. This is organic chemistry, study of carbon-containing molecules. Forming a carbon-carbon bond is going to be really, really important to that. So what we'll see is, for example, these acetylides are actually really important in chemical synthesis as we begin to build these up. So, okay, the one thing that I didn't mention, and I don't know that we'll have time, and maybe I'll introduce at the beginning of next class, but you can make these alkynes directly. I'll talk about it next week. I don't want to go through it too quickly. So, yeah, these.